Good afternoon, everyone. I am Dr. Sharat Chandra Tripathi. I am your host for today's interaction, and I have Dr. Pradeep Kumar Keshav with me. We are here to facilitate your interaction with today's speaker, Dr. Helen Elizabeth Mason. VIT Bhopal University is celebrating National Science Week during 25th of February to 3rd March 2022 to commemorate the discovery of Raman effect by Sir C.V. Raman. This event is catalyzed and supported by National Council of Science and Technology Communications, NCSTC, DST New Delhi, and Madhya Pradesh Council of Science and Technology, Bhopal. On behalf of VIT Bhopal University, I welcome you all to the 6th lecture of this planned lecture series, which is going to be delivered by Dr. Helen Elizabeth Mason. She is Emeritus Reader at University of Cambridge, and she will be speaking on solar spectroscopy in ultraviolet and X-rays. Dr. Helen has joined us, and we are quite privileged and delighted to host you, ma'am, on this platform of VIT Bhopal University. We will have the lecture first, and then we'll open the session for Q&A. You can post your questions in the chat box, which can be asked after the talk. I request my fellow colleague, Dr. Pradeep Kumar Keshav, to introduce our today's speaker to the audience. It's over to you, sir.
Thank you, sir. Dr. Helen Mason is a solar scientist at the University of Cambridge. Her field of research is solar physics, in particular the ultraviolet and X-ray spectrum of the sun. She has worked on many joint UK, NASA, ESA, Japanese, and Indian space projects, including SOHO, Hinode, and SDO, Chandrayaan. Recent solar space observations have completely changed our view of the sun. Helen has always been keen to convey her passion for solar physics to the public and to students. She has given many public lectures and worked closely with UK schools. She has close scientific links with colleagues in India, especially at IUCAA Pune. She works closely with teachers and students throughout the UK. Most recently, the project's sunspaceart.org. She has also worked with educators, teachers, and school students in India. In 2014, Helen was awarded an OBE for her service to higher education and to women in science, engineering, and technology. In 2018, she was awarded the Royal Astronomical Society's Annie Maunder Medal for Outreach. We welcome again Dr. Helen Mason. It's over to you, ma'am, now.
Thank you. I'll just share my screen. It's a great honor to be invited to give this talk, and I thank you for the invitation. I have worked closely with colleagues in India for many years, so India is my second home. And I regret that I have not been able to visit there recently, but I hope to do so very soon. So I study the sun, and here's a picture of the sun taken from space. So this is a picture from the Solar Dynamics Observatory. And you can see on the side of the space sun, a huge explosion, and I'll explain a little bit more about that. So I'll share with you some of my work. As it said, I work at the University of Cambridge. Okay, this one isn't moving on, so I'm just going to stop this and do it again. Okay, sorry. Okay, I think, okay, I'm going to have to just, sorry, okay. I'm just going to have to close and start again because the slideshow is not moving on. So just let me go to that again. Sorry about that. We should have left it as it was.
Screen, not only the file.
Just 1 second, please. Yep, sorry. Technical difficulties. Always a problem. Okay, I'm going to try the share screen again. It was working, as they would say, it was working previously. Okay. Okay, should work this time, I hope. Okay, right, let's hope. Fingers crossed, everybody. Hey, okay, there we go. Technology has been quite a challenge this past 2 years, but we'll get the better of it. Okay, this celebration in memory of Sir C.V. Raman, very famous Indian scientist, and he has many quotes that he has made, very deep quotes. I just wanted to take one. The essence of the scientific spirit is to realize what a wonderful world it is that we live in. Now, it doesn't seem quite that way at the moment, but let's hope. Let's all be hopeful for the future, and let's look towards a future. And many of the people listening here can help us achieve that future. I wanted to dedicate this talk to a dear friend, Rathna, who is the director of the planetarium in New Delhi, the Nehru Planetarium. And sadly, she died of COVID in the summer of 2021, a great loss. She was a wonderful person and reached the hearts and minds of many young people with her outreach work. Indeed, I had the privilege to visit the planetarium in 2015, and here we're engaging with some school students doing some solar work, projecting a solar image, and you can see Rathna there on the right-hand side, and I'm there as well, and I gave a talk at the planetarium. A great honor to be invited to give a talk there and to interact with the students. So let me turn to the solar science. I've had a very privileged and life in solar physics. I've worked on many space projects, and these are just a few of the most recent projects I've worked on. SOHO, has been operating for over 20 years now, almost 30 years now, and is still operating, and I was a big part of the work that I did. Others there in the ultraviolet and X-rays, the traces and the ultraviolet rests in the X-rays. Hinodi, I'll tell you a little bit more about. Stereo Solar Dynamics Observatory, I just showed you an image from. IRIS, a spectrometer, and more recently Parker Solar Probe and Solar Orbiter. So obviously I can't cover all of the instruments and satellites I've worked on, but I'll just give you a flavor so you understand a little bit more about the work that I've been doing. Now, I don't work alone, and this is part of the team that I've been working with, both past members of the team in Cambridge and some current members of the team. And you'll see there me standing next to Professor Durgesh Tripathi, who I'm sure many of you know, who worked in Cambridge for many years as a postdoc and is now at IUCA, head of the solar group there. Also, on the other side is Saga Mule, and she was my last PhD student and is now working in Glasgow University, and I'll say perhaps a little bit about her work. Other members of my group are now professors in the USA. My first student on the left-hand side there, Peter Young, and Steve are both next to him, are both professors in the USA. And the man with the white hair there is Giulio Delzano, who I've worked with for many, many years. And I'll say a little bit about the work we've been doing together. So the sun is just a star like many other stars. It's a middle-aged star, about 4.5 billion years old. It's huge. And here you can see some sunspots on the sun, and I'll tell you a little bit more about those in a minute. But if you see the one almost in the middle there, I don't know whether you can see my arrow, but that's about the size of the Earth. So you can fit over 100 Earths across the sun and 1 million Earths inside the sun. The sun is huge. It's a long way off. It takes light just over 8 minutes to reach us. It's massive. And the surface temperature is around about 6,000 degrees. The energy is produced right in the core of the sun by nuclear fusion, turning hydrogen into helium. Through Einstein's equation, a little bit of mass is turned into a huge amount of energy. It then takes quite a long while to move out through the different layers of the sun, through the radiative layer, and just beneath the surface, there's a convection layer. So the core is 15 million degrees, and the surface is around about 6,000 degrees. And here is the latest images of the surface of the sun. And you can see the convection. These are taken with a very new telescope called DKIST in the States, over in the USA, which is producing some amazing detailed images of the sun. It's built by the National Solar Observatory and was first light, the first observations were in 2019. So, and there it is on Hawaii, on the mountains, high up in the mountains. So you can see a lot of structure there in the convection zone beneath the sun. But if we go back in time and think a little bit about these sunspots, they were observed a long time ago. They were observed by the ancient Chinese in the early morning mist, but they were studied by Galileo, one of the scientists who was based in Italy. And you can see here Galileo's actual drawings of the sunspots. I say to you, never look at the sun. The sun is much too bright. You must never look at the sun, but you can project an image of the sun or use a very special solar telescope. And here an image of the sun is projected, and Galileo has drawn the sunspots that he saw. And as you can see, the sun is spinning on its axis. So he associated those sunspots with the sun. Here we see a lot of sunspots on the sun, and when there's a lot of sunspots on the sun, then we also get a lot of activity. So the sun goes through phases of activity, and that activity, those explosions that take place on the sun, solar flares, coronal mass ejections, can come towards the Earth, and they can cause the beautiful northern lights, aurora borealis or aurora australis in the south. Here again, you can see the sun spinning. It takes about 25 days to spin around once at the equator, and it's slightly slower at the poles. It's 30 days. So the sun is a gas, so it doesn't have to spin at the same rate in all latitudes. Now, as I said, these number of sunspots varies, and it has a 10-year period of variation. Along the bottom there, the bottom axis, the x-axis is the year from 1900 to 2000, and along the y-axis is the sunspot number, the number of sunspots, and you can see that it goes up and down with about a 10-year period. So there's no sunspots, there's a lot of sunspots, there's no sunspots. At the moment, the sun has been quiet, but is just beginning to have more sunspots and get more active. So it's just beginning to go into an active phase. Now, I wanted to share with you some information about the observatories in India, in particular the solar observatories. And here the Kodaikanal Observatory in Tamil Nadu was founded in 1899, and it has made continuous observations of calcium-2 and H-alpha for over 100 years. Now, all of the data that it has is now fully digitized and available for the public to look at. The Evershed effect, that is motions in the sunspots, were discovered there in that observatory. In Udaipur, we have the Solar Observatory, a beautiful observatory in the middle of the lake in Udaipur. And it was founded in 1976. And I'll say just a little bit more about that in a minute. It has a very advanced solar telescope called the Multi-Application Solar Telescope, making observations there. It uses a lake. On a lake, the seeing is quieter, is better because the air is calmer, and that's why it's in the middle of a lake, like Big Bear. There's also the National Large Solar Telescope planned, and that will be in Merak village in Ladakh. And that's sponsored by the Institute, Indian Institute of Astronomy, and ISRO, the Indian Space Research Organization. So here's an image close up of a sunspot, and I can run it again. I'll just see if I can. Let's see if I can run it again. Oh, here we go. You can see there the motion. So the Evershed effect looked at these fine scale motions coming out of the sunspot in the penumbra area. And as I say, those were discovered by Evershed in the Kodaikanal Observatory. And here is a visit that I made to Udaipur, when I also visited the physics research lab in Ahmedabad, and went with Jerry and Santosh up to visit the observatory. And here you can see various members of the observatory, including Professor Nandita Shrivastava, who's a very famous solar astronomer. And there she's showing me some of the historic documents from the observatory. And there you can see the MAST telescope and a sunspot observed with it. I'm not going to go into details, but India also has several solar radio facilities producing wonderful data that can be used for solar models and observations. I was very privileged in 2016 to be invited to lecture at the introductory solar workshop organized in Kerala. And here you can see us all at the solar workshop. It was a very auspicious occasion, very great occasion, and the students produced posters on their solar work as well. The students from all over India participating there, and you can see Dergish and Venkat and Nandita also attending, and others. So let me go back again in time a little bit to one of my favorite astronomers, Sir Isaac Newton. He's a favorite astronomer because he lived in Cambridge, but also because he was not only interested in gravity and telescopes. He built his own telescope, which was a reflecting telescope with mirrors, and there you can see a drawing of it. But he was also interested in the nature of light. So he studied light. He looked at the colors that were obtained when light goes through a prism. And he realized that the white light, that we call it, is made up of the different colors of the rainbow. So he's a favorite astronomer of mine. And sometimes when I walk through Cambridge, I think, well, maybe I'm walking in his footsteps. So maybe some of his brilliance will rub off on me, still be there. So we don't have to stay in the visible wavelength. That's the wavelength that we can see. That's the light we can see. But if we go beyond the violet, we get to the ultraviolet and the X-rays. And if we go beyond the red, we get to the infrared and the radio. But we can also use a very special instrument, which is called a spectrometer. And a spectrometer has a slit, and a spectrometer can be used to break the light up, not just into the colors, but if we have a gas and we pass the light through a gas, then some of the light is absorbed at certain wavelengths. So we call that absorption, or the dark lines of particular wavelengths. And I'll say a little bit more about that. Or if we have a gas and we heat it, then we can look at the light that comes from that gas and we get emission lines at very specific wavelengths. And this gives us a huge amount of information. This is a spectrometer, and this is what I specialize in, getting information from the light, from the gas, as the light passes through the gas, or actually emitted by the gas itself. So if we looked at a spectrum of different elements, now I should say the sun is mainly made up of hydrogen and helium, but it has tiny little bits of lots of other elements as well. In fact, helium, and there's an image of emission from helium, we just choose that narrow wavelength band, and that's taken from the Skylab observations down the bottom there, and you can see a huge explosion again on the side of the sun. So you can see there emission lines from hydrogen, helium, nitrogen, neon, argon, and mercury, and you can see that they're all different for different elements. So this gives us a way of finding out the composition of the sun or of the stars or of whatever we're looking at from the light using this spectrometer. I think it's a little bit like your fingerprints, which are all unique, or a little bit like when you go to a supermarket and you have a little bar chart which is scanned, and that tells you what you're buying and how much it costs, or at least it tells the person in the checkout. So this is a unique way of finding out what the sun is made of, or what the stars are made of. But there are other aspects to it as well. We can use these spectral lines in other ways as well. These are the visible lines, but we can look at these spectral lines in the ultraviolet or in the X-rays in different ways. So here is a total eclipse of the sun, and I'm not sure how many of you will have seen a total eclipse of the sun. It is an awesome experience, and I've been privileged to see several total eclipses of the sun, most recently in the USA in 2017, when the eclipse went right across the USA. Now, what happens is the moon is exactly the right angular size to block out the disk of the sun. Of course, the moon is not the same size of the sun, but it's much closer to us, and it's just the right size to block out the main disk of the sun. This is in visible light, in white light, and the disk of the sun is 1,000,000 times brighter than that light that you can see during the eclipse. Now, this light is called corona, or a crown of light around the sun, and it is simply spectacular. And you can see it's also very structured. So if you look carefully there, you can see it's very structured. There's a lot of structure. And what is happening there is the structure is tracing out the magnetic field on the sun. So that is the solar atmosphere that you're seeing there, the solar corona. It's highly charged, and it's tracing out the magnetic field of the sun. But when people used a spectrometer to look at that corona, they were mystified. They couldn't understand for many, many years what they were seeing. They saw some very strong emission lines in the visible. They saw one in the green, one in the yellow, and a red line, and they couldn't explain what element these lines had come from. So helium is named after Helios, for the sun, which was discovered first of all on the sun. So they invented a new element called coronium, which comes from corona. They thought these lines were due to a new element. However, the scientific theory didn't work. Not all scientific theories work because they couldn't fit coronium into the periodic table of elements, the pattern of all the other elements. And it took them a long time and a lot of very careful laboratory work and analysis by Edlen and Grotian and others to work out that actually these lines are just due to iron. That's just normal iron, which normally has 26 protons in the core, 26 electrons going around the nucleus. But although the surface of the sun is 6,000, they realized that actually the corona was very, very hot, 1,000,000 degrees. And because it was so hot, the atoms had bumped into each other and knocked the electrons off. The hotter the gas gets, the more the atoms bump into each other and the more electrons are knocked off. And in fact, the green line is due to iron, which has 13 electrons knocked off. So it's just left with 13 electrons. We call this Fe plus 13, or another way, Fe Roman 14. So this is what the green line was due to, and this is how they knew that corona was 1,000,000 degrees. Now, the coronal lines are very important to me because this is what I studied. The coronal visible lines is what I studied for my PhD thesis, my graduate work back at University College London many, many years ago. And there is my supervisor, Professor Mike Seaton, and he's talking to Dr. Alan Burgess, who was also my supervisor when I moved to Cambridge, a very eminent solar scientist. Sadly, neither of them are with us any longer. But I carried out the first detailed calculations for those coronal forbidden lines, iron 10, 11, 14, and other lines. And the first calculations that enabled people to interpret those lines and to understand the intensity of those lines. So if we look at an atom, it's got a nucleus in the core, it's got a lot of electrons going around that nucleus, but those electrons can be in different energy states. They can be in the lowest state, but they can also jump into higher states. And when they jump from one state to another, they give out a little packet of energy. Through quantum mechanics and atomic physics, we know that they can't be in a continuous number of states. They have to be in specific states. And so there's the specific packets of light at specific wavelengths. So H is Planck's constant times nu, the frequency, and that's the energy that's defined. So that defines the wavelength of light that's given out. And this is a unique feature of all the atoms. And as they get ionized, they get different energy levels and different jumps. Because the corona is so hot, it emits very, very strongly in the ultraviolet and the X-rays. And this is a picture, an image taken from Yoko, which was a Japanese satellite. We've worked a lot with the Japanese colleagues as well. And it's a picture in X-rays. So everything you see there is 1,000,000 degrees. So one of the big questions in solar physics is, why is that corona so hot? We don't expect it to be that hot. If the surface is 6,000, why is the corona so hot? And you can see some very bright regions, which are where the sunspots are. They're called active regions. And you can see some very dark regions, for example, at the top. And that's where the magnetic field is open. And the gas, we call it a plasma, which is an ionized gas, flows out into space, into the solar wind, into the fast solar wind. This shows you what that X-ray image of the sun looks like going from solar minimum, when it's quite dark, on the right-hand side, to solar maximum, when there's a lot of X-ray intensity during the peak, when there's a lot of sunspots. So let me turn to SOHO. SOHO was possibly one of the best solar observatories we've had. It produced some amazing results, looking at the core of the sun through vibrations on the surface, looking at the atmosphere of the sun, and looking at the solar wind that flowed off the sun. So SOHO, as I say, was launched a long time ago, 1995, and it's still operational, though some of the instruments are no longer used because we now have better observations. So as I say, it was used to study different aspects of the sun. And I worked on it for a very long time, working with colleagues all over the world, and colleagues in particular at the Goddard Space Flight Center at NASA. And here's an image of the sun, a movie of the sun, taken in the ultraviolet. Now, the sun is not green. We know the sun is not green, but we can't see the ultraviolet. So this is an image taken with a camera that can see the ultraviolet, and we've colored it green. Again, you can see those very bright regions we call active regions. You can see dark areas we call corona holes, holes in the corona, where the solar wind is flowing out, and you can see a lot of activity all over the sun. This is taken in a line IN12, sensitive to a temperature just above 1,000,000 degrees. And here's an image taken. We also had instruments on SOHO which could look at the surface of the sun, and this is the magnetic field on the surface of the sun. So those dark and bright areas are where the sunspots are. The sunspots are areas where the magnetic field is very strong, but you can see small patches of black and white all over the sun. So we're able to measure the magnetic field at the surface of the sun, and we're then able to see how that relates to what we're seeing in the atmosphere of the sun. I wanted to just tell you about another instrument called Hinode that I've worked a lot on. That was launched in 2006. And in particular, I worked with the team which led the spectrometer called ICE, the EUV imaging spectrometer. And the principal investigator, that's the person who led this instrument, Louise Hara, is in the center of the picture there, from the Mullard Space Science Laboratory with other members of the team. So Hinode had 3 instruments. It had an optical telescope, solar optical telescope, which looked at the surface. It had ICE, the spectrometer, and then it had an X-ray telescope. And it's still being used. We're still using it to make observations of the sun, and we're still analyzing the data from it. And what we're able to do, it has a slit, and we're able to get a spectra at each position along the slit. That's called a stigmatic slit. And we're able to build an image by rastering the slit across an area. And here you can see a spectrum from just one point along that slit. We get a lot of data, a lot of complicated data, and we need to be able to analyze that data. We cover a lot of wavelengths. So in order to analyze that data, I combined with my colleagues in the USA and in Italy, and this is taken as a picture of quite a long time ago, as you can see now, we were all a lot younger, from in our Eclipse Observatory in Italy, in Tuscany. And we brought together a huge atomic database, which solar scientists now throughout the world use to analyze not just spectroscopic data, but other data from imaging instruments as well. Our first release was in 1996, and we're still updating, we're still working on this database and making it available for everybody to use. This means they don't have to go back and look at all the papers in detail. They have a facility there that enables them to analyze the data that they're getting from the spectra. We updated recent release version 10, and it's been extremely successful with over 3,000 citations. So it's used universally now. It's a very widely used database, and I and Candia, one of the founders, sadly, Brunella Monsignor Fassi, the other founder, is no longer with us, but that's the team that we work with. And here's a spectrum from the Hinode ICE instrument, and you'll see there's lots of spectral lines. This goes from 170 angstroms to 284 angstroms, and you can see lots of lines from iron, from silicon, from sulfur. So we get a very complex spectrum, and we need to analyze from that spectrum. We can get lots of information, we can get density, we can get temperature, we can get the amount of material at different temperatures, we can get the element abundances, as I've said. And another interesting thing we can find out about is motion. So the spectral lines shift slightly if the plasma is moving. If it's moving towards us, they shift towards the blue, and if it's moving away, they shift towards the red. So we can get from the line profiles, we can get information about the motions and about the broadening, which tells us about other features that we can analyze. Now, as I said, when we look at the ultraviolet, we see these beautiful large loops of gas. This is in an active region. And if we think about a magnet lying there on the surface of the sunspots are where the magnetic field is rooted down beneath the surface of the sun. So above it, we see the active region, bright loops in ultraviolet and X-rays, and beneath the surface. And on the surface, we can see the sunspots. Now, the magnetic field on the sun is formed beneath the surface, perhaps possibly in an area between the radiative and the convective zone. And as the sun rotates differentially, it rotates faster at the equator. It gets twisted round and then eventually pops out through the surface with these huge loops where the sunspots are. There's an important process called magnetic reconnection, which I wanted to tell you about, because we believe this is the way in which energy is released in the corona. It's channeled up from beneath the surface, and then the magnetic field gets twisted. It doesn't like being twisted, and it changes back to a lower energy state. As it changes, it releases magnetic energy into thermal and kinetic energy. This can happen on small scales, we call these nanoflares, or it can happen on large scales, which gives us very big flares. On small scales, we think this is how these loops of hot gas are heated, and Parker was one of the first people to suggest that the magnetic fields get twisted up, and as they untwist, they release energy. And here's an observation from ice. On the left-hand side, we see the intensity of a particular line. Then we see the Doppler shifts, and we can see material flowing out where it's blue, and we believe that's flowing out into the solar wind. So we try and model these regions to see what's happening in these regions. Another more recent observatory called the Solar Dynamics Observatory, which we've already mentioned, was launched in 2010. And that observes the sun in several different wavelength bands, which are sensitive to different temperatures. And it has a cadence of images every 12 seconds. So here we can see going from a low temperature at about 5,000 degrees up to a very high temperature to 10 million degrees. We can see different images of the sun every 12 seconds in these different UV wavelength bands. And this enables us to model different features on the sun and track the heating and the cooling. And here you can see beautiful images of those big hot million-degree loops in the ultraviolet as the sun rotates into view, taken from the Solar Dynamics Observatory. Now, sometimes magnetic flux can erupt from beneath the surface, and this is just a model. And as it does so, it reconnects with overlying magnetic flux and can heat and produce energetic events. This is a small type of event called a jet, which was studied by Sargam for her PhD thesis. And we're able to model these jets and to compare what we're observing with what theory predicts as the magnetic field erupts from beneath the surface. And these could be very important features in the solar wind that I will talk about later. A very large explosion called a solar flare happens quite rarely. We've had the largest is called an X-class flare. We've had 1 or 2 X-class flares recently. They're more frequent when the sun is very active. Here's an image taken from Carrington and Hodgson, the visible, of the very first flare that was seen in the visible. And you can see the picture that they drew of it when they projected an image in their telescopes. A flare is a complex process, and we believe that structures erupt and then magnetic reconnections happen below those structures, forming large hot loops of up to 10 million degrees. So we can study this in the X-rays and in the ultraviolet. And here's an example of a flare taken with the ultraviolet, and you saw the flare go off, and then you can see these large, very hot structures growing in time. Sometimes material can be ejected at great speeds. We call these coronal mass ejections, and they can be billions of tons of material moving at speeds of up to 2,000 kilometers per second. Here the sun is blocked out. The sun is actually where this white circle is. It's blocked out, but here you can see material moving out into space. And here's an example of something lifting off and then moving out into space. I'll run that one more time. You see something lifting off from the sun and moving out into space. We call these coronal mass ejections. We want to understand how they happen, when they happen, why they happen. And this is because if they come towards the Earth, they can be problematic for us. Fortunately, the Earth is protected by its own magnetic shield. This is not to scale, but here we can see a feature coming from the sun hitting the Earth's magnetic field. But it can disturb the Earth's magnetic field, causing reconnection behind the Earth, and this can project particles back down, mostly to the polar regions, causing the beautiful northern lights. This picture of the aurora is taken from the International Space Station. You can see parts of the International Space Station. And although very beautiful, they can also be problematic in our technological age. They can harm astronauts if they're out in space. So if an astronaut in the International Space Station is doing a spacewalk, for example, they have to check the space weather, first of all, to make sure there's no storms, solar storms. They can affect satellites, knocking them out. They can cause electricity blackouts. They can affect high-flying aircraft and other things. So we need to understand, this is called space weather. We need to understand the interaction of the sun with the Earth. Now here's in the background there, you see an image from Yoko, but here you can see along the X-axis is the year, going from 1990 right up to 1921-22. And this is the Sunspot Cycle that I showed you earlier. And you can see that at the moment, we've been through a minimum of activity, a very long minimum of activity. And now we're on the rise and we're seeing more activity and sunspots. So as I said, recently, there have been 2 missions to try and understand the sun, what's happening on the solar surface and how that interacts with the Earth. The first one that I'll mention is NASA's Parker Solar Probe. This is named after Eugene Parker, who did a seminal piece of work on the solar wind that initially nobody believed and tried to publish it, but the authors, the referees rejected it. But the editor, Chandrasekhar, said, no, what he's done is right, it's valid, I'm going to publish it. And now that is one of the premier papers in the field that everybody refers back to. So Parker is there watching the launch of a satellite named after him. It's very rare, if not ever, to name a satellite after somebody who is living. So he was able to watch the launch of the satellite. ESA, European Space Agency, and NASA have also launched a satellite called Solar Orbiter, which isn't going quite as close to the sun as Parker Solar Probe, but is going very close. But it has some instruments which will be used, a spectrometer as well, to study the surface of the sun in more detail. So that was launched just before lockdown and had to be tested and operated from home during the lockdown period. An amazing feat. It all ran to schedule and now is doing science operations. And during March this year, there will be some coordinated observations with other observatories from Solar Orbiter and lots of other instruments. So as I said, Parker Solar Probe it stays in the ecliptic plane, whereas Solar Orbiter goes out and will observe some of the polar regions. Parker Solar Probe goes very close to the sun, going into that corona. Solar Orbiter doesn't go quite as close, but it does go close. Of course, they have to be built with special materials to go close to the sun. Parker Solar Probe has in situ. That means it's sampling the solar wind that's flowing off the sun and any of those structures, coronal mass ejections that are coming towards it. And Solar Orbiter has both instruments to sample the solar wind, but also has instruments, we call them remote sensing, to study the surface of the sun, the origin of some of the features that it's observing. One interesting thing that it's observed so far is called switchbacks in the magnetic field, and they think that these might be related to those small jet-like activity that I was talking about earlier that Sargan was studying when material is shot out into the solar wind. It's just one of the science. I don't have time to cover all of the science that's observed or been reported from Parker Solar Probe or Solar Orbiter, but that's just one. As I said, I'm particularly interested in Solar Orbiter for 2 reasons. This is an X-ray spectrometer called STIX that we're looking at data from, but also there's a spectrometer called SPICE, which, as you can see, has lots of spectral lines there, and we're able to get a lot of information about abundances in the region that we're looking at, and we can trace those abundances into the solar wind. So here you can see below observation from SPICE, and here you can see an instrument which is sampling abundances in the solar wind. So let me turn, I'm almost finished, but let me just turn to some more recent work we've been doing. One of the positive spin-offs of the lockdown is that we use Zoom a lot more, as we're using now, and we're able to communicate better with other people on the whole. And we've had a collaboration, a Royal Society collaboration with our colleagues at PRL Ahmedabad. And this has been related to an instrument that they have on Chandrayaan-2. And this collaboration has been very successful, resulting in many research papers. And we're very grateful for our colleagues to be able to work with them in this way. And we have regular Zooms once a week or once a fortnight to discuss the solar physics, to discuss the observations. Of course, Chandrayaan-2 is looking at the moon, so it's actually looking at the fluorescence of the moon, but we're particularly interested in the X-ray spectrum that comes from the sun, which they're observing. So here are the collaborators, Santosh, Biswait, Nathan, Jerry, and others working with the team in Cambridge, Julia, myself, Yamini, and Umila. So a very successful collaboration, now has been running for 2 years. It was launched, here's the launch of Chandrayaan-2, the orbiter, in 2019. And just a sample of some of the data that they're getting in the X-rays. Obviously, this is complex data and needs a lot of very careful analysis. But here you can see a spectrum in the X-rays for different features. I think the magenta here is the quiet sun, and as you go up, these are more active. M2 flare is a stronger flare that we're seeing. And what you'll see is a spectra here. You can see bumps which are representative of bunches of lines from different elements. So we're able from this to determine lots of plasma parameters, the density, the temperature, the emission measure, which is distribution of material as a function of temperature, and the abundances, and able to get a lot of information from these spectrum. And as I say, if you look at the XSM website, you'll be able to see references to the many papers that have been published on this data. Also some in collaboration with us. And here you can see this is as a function of time, date along the bottom here, and you can see the X-ray emission, and you can see how variable it is. Now, this instrument is very sensitive, much more sensitive to the X-ray emission than previously instruments, and has a very good spectral resolution. So we're able to detect some what we call microflares, very small flares that are happening on the sun. And this helps us to understand the heating of the solar corona. So we're able to observe the sun during quiet periods and also during periods of more activities and indeed stronger flares. And we're able to detect the elemental abundance changes, and we found some very interesting results with regard to the solar flares that we've been looking at down the bottom here. Because it's a full sun, because it's looking at the full sun, we can't get spatial resolution, but we can use observations, for example, from the Solar Dynamics Observatory to determine where the regions are that are emitting the X-rays. So we have to combine observations from different instruments, from the XSM, with the Solar Dynamics Observatory, and we're also combining it with Hinode observations and also with observations from Solar Orbiter from the STIX instrument. So finally, sorry, I'm running over just a fraction. I wanted to say that I have had a very, very fruitful and successful collaboration with my colleagues, Ayuka, and here you can see Professor Dergesh Tripathi's group. When I visited 1 year, I try to visit each year and collaborate on scientific grounds. And here's Sargam. Sargam was originally a member of his team, and then she came to Cambridge to do a PhD with me. And we've worked on many papers and publications. And also, Dergesh is leading one of the instruments on Aditya L2. Now, I forgot to say Solo is at the Aditya L1 is at the L1 Lagrange point between the sun and the Earth, and it orbits the sun. And Aditya L2 will be at the same position. And that should be launched fairly soon, either this year or early next year. I also worked with Ayuka Saipop a lot when I'm over in India, and I really enjoy working with children in the schools there. And there we're doing some solar projections and some solar work. So Aditya L1 has a whole suite of instruments, X-ray instruments, also some instruments being built by PRL and IIA and other people. It's obviously the Indian ISRO mission. It's the first major solar mission by ISRO to observe the sun. I don't have time here to go into details, but I'm sure others will tell you more about Aditya. It's very, very exciting mission. The SUIT instrument, the Solar UV Imaging Telescope, is being led by Yuka, and here we can see it being built and in the clean room, and it's now on the satellite. So it will be looking at the chromosphere, the layer just above the solar surface, and the transition region. So finally, as I said, as was said in the introduction, I do a lot of work with schools, and one of the projects we've had is to use both scientists and artists to work with schools. And this is a project called Sunspace Art. And if you go to that website, you can see some of the workshops that we've run with over 150 schools here in the UK. And what we do is we do a science engagement activity, perhaps the sun, perhaps the solar system, perhaps space. And then the artists will use their artistic techniques, and the students will then produce works of art which illustrate the science that they've been learning. It's been hugely successful with some tremendous feedback. And I just want to thank you. I have really enjoyed working with my colleagues in India, both in the scientific capacity, but also with the schools. So I wanted to thank you for hosting me and for engaging with me.
Thank you. Thank you for such a great talk on solar spectroscopy, starting from the Newton's days to the modern days experiments and space missions. And you have made the things very easy for a layman while explaining the basics of the science behind the solar eruption, especially the role of magnetic fields in the development of solar transients and their interaction with geospace. So it's a time for question and answer session. So I'd like to request my fellow colleague, Dr. Pradeep Kumar Keshav, to take a few questions from the audience for the discussion. It's over to you, sir, please.
Thank you, sir. Thank you, ma'am, for a nice talk. And we have some questions from the audience. Akanksha Jha, she asked, why is there variation in the number of sunspots?
Yeah, that's a very good question. Thank you for that question. Now, as I said, the magnetic field is produced beneath the surface and then erupts through the surface. And then it kind of dissipates with all of these flares and flows out into the solar wind. And then it starts to form again every 10 years. This is called the solar dynamo, the way in which it's formed beneath the surface. Why it's 10 years is not entirely clear. And I'm not an expert in that field, but people are studying that and they're very interested to learn about that. There are complex motions also going on beneath the surface of the sun. It's the area of study there is called helioseismology. So it's one of the things we're trying to understand in detail. We can predict what's happening and we know in general terms what's happening, but the details of it are still being worked out. It also happens on other stars on different timescales, but it's, as I say, the scientists are still trying to, maybe one day you can work on that and tell us why it's happening exactly. That would be wonderful.
Thank you, ma'am. The second question from Purvika, and she wanted to ask you how differential rotation is impacting solar activities.
Yeah, so it's this differential rotation, the fact it's spinning faster at the equator than it is at the poles, which is twisting that magnetic field around, and then it erupts through the surface. So it definitely impacts solar activity. So when there are very few sunspots, the activity is very low, very quiet, which is what we saw a few years ago when Chandrayaan-2 was first launched. But as the activity builds up and the magnetic field comes from beneath the surface in those big arches, then we get more activity. It's twisted up and it likes to untwist. And as it untwists, then it produces lots of solar flares and coronal mass ejections. So there's a definite link between the differential rotation, which is causing the twisting up of the magnetic field beneath the surface, and the activity that we see above the surface in the corona and the explosions. So definite link there. In many cases, we understand better because we get better observations and we get better theory, and with better computers, we can now model things not just in 2 dimensions, but in 3 dimensions. So we're getting a better understanding of what's happening, but we still sometimes lack the details because these processes are very complicated, and the mathematics is very complicated to combine the different mathematical tools that we use to understand, and then to compare those with exactly what we're observing. So it takes scientists, they don't work in isolation, they work together as a team, bringing together theoreticians and observers to try and understand what's happening. But definitely, there's a definite link there.
Thank you. One very basic question from the audience, and he is asking that what are these long thin structures that are seen during the total solar eclipse?
Oh, the long thin structures going out into space?
Yeah,
yes, those are streamers that we see during a total eclipse, and those are streamers above an active region where the magnetic field stretches out into space. So what they're doing is they're showing us the magnetic field stretching out into space, and some of that would probably be going out into the solar wind. So one thing that we're trying to understand with Parker Solar Probe and Solar Orbiter, we know that in the place where the magnetic field is open at the poles, the fast stream flows out, but we want to understand more around active regions. The slow solar wind is very intermittent, it's very bursty, and we want to understand where that's coming from. So we think that those are regions where that other component of the solar wind is coming from. So I think that's what he meant by the long streamers, yeah?
Yeah, thank you, ma'am. Suresh Babu, a student from VIT Bhopal, and he is going to ask some questions. Suresh, you can unmute and you can ask.
Yes, sir. Thank you, sir. Hello, ma'am. It was a nice lecture. Thank you very much for that. I want to ask this doubt. How alpha waves are influenced in the coronal heating?
Okay. Yeah. Okay. I haven't really mentioned, I mentioned nanoflare heating, but I didn't mention alphane waves. Now, in recent years, it's become more and more the case that we see waves, we detect waves in the solar atmosphere. And these alphane waves could play a key role in the heating, in transferring energy, either from beneath the surface or up into the corona, or during some of the reconnection events, then there might be alphane waves. So certainly in the solar wind, wave heating has been observed for quite a long time, and we can detect this in different ways. We can detect it because it's a wave. We can detect it in the broadening of a line, for example. So yes, I haven't mentioned waves, but there's a school of thought which thinks that waves may play a prominent role. One of the problems is that in the past, they haven't been able to get enough energy or to dissipate that energy once it gets up into the corona. So that's what people are working on, the dissipation of the waves that we might see in the solar atmosphere.
Thank you, ma'am. I have one more doubt. We have learned about this magnetic reconnection, how the energy of magnetic reconnection is connected with the acceleration of electrons.
Yes, that's another very important point, and I haven't mentioned that either. Obviously, when you get magnetic reconnection, then you get some very, besides heating, you could get some very fast particles. We call those non-thermal particles that could be produced. And one of the researches that we're doing is trying to search for non-thermal particles in the spectral lines if we can detect them. And we have several papers in which we think we have identified non-thermal particles. I mean, in flares, we often see these produce hard X-rays, so they come out in the hard X-rays, we see non-thermal particles. But in smaller events, in smaller heating events, we're searching to see if we can see them when this magnetic reconnection happens. And we think we've found some evidence for that. So a very good question too. I see someone's asked a question about what kind of features do different wavelength telescopes reveal? And that's quite an interesting question. So could I answer that question?
Yes, ma'am. Go ahead, please.
Okay. I think it's a really interesting question, because why do we have so many different instruments? Why have we got radio? Why have we got ground-based observatories? Why have we got space? Why don't we just have one instrument that does it all? And this is because each instrument does see different aspects of what we're observing. So what we do is we don't just use one instrument. First of all, we'd use the whole observatory. So for Hinode, for example, we wouldn't just use the spectrometer. We combine the spectrometer with the X-ray instrument, with the instrument that's looking at the observations of the surface of the sun. But we also combine these with detailed observations from the ground, for example, because we can get very high spatial resolution from some of the ground observations as well, or the radio can tell us different things. So each instrument tells us somewhat different things, and the maximum amount of information we can get is by combining. We call these coordinated observations, combining the information we get from different instruments. And this is sometimes very difficult to do because the instruments have different characteristics, they're very complicated, and we need to make sure that we're looking at the same region to start off with, or doing things like that. But it's an interesting question. Why do we, what kind of features do different wavelength telescopes reveal? They can be used to study the same feature, if it's an active region or if it's a flare, but they will be showing us different parts of that, the high energy part or the lower energy part. So it'll be, we're looking at an elephant, but some parts might be looking at the tail or the head or the color or whatever. So we're looking at different aspects of it.
Okay, there is one more question that you can see in the chat box by our fellow colleague Xavier Suresh. Can you comment on the artificial sun?
Could I comment on, sorry, could you say that again?
Artificial sun.
Artificial sun.
Yeah.
Do they mean diffusion research? Is that what they mean?
I think so.
Okay, yes, that's a very interesting point. I said the energy in the core of the sun is produced by nuclear fusion. Now, if we could harness that way of producing energy here on Earth, we would have a relatively clean nuclear fusion reactor, and that is being done. So we can already turn hydrogen into helium here with the JET laboratory, for example, which is an international collaboration in Cullum. You use a torus to do that. They have to confine it with a magnetic field. But there's another project called ITER, ITER, in France, which India is also involved in, which is an international collaboration to produce a commercial energy. So commercially, at the moment, we have to put in more energy than we get out, which isn't very commercially viable. But what they want to provide is some way of commercializing this so that we can produce energy in that way. So fusion has already been reproduced here on Earth, but we now need to make it so that we can produce energy. And I think if we're looking at a sustainable future, it's always been about 10 years away, but it will be in the lifetime of the students who I'm talking to now that we will have nuclear fusion reactions. And you need to understand the difference between the nuclear reactors we have now, which are fission reactors, which have a lot of problems getting rid of the radioactive waste, and a nuclear fusion reactor, because generally people won't understand that and they will be afraid of it when they don't need to be afraid of it. It's perfectly safe and it doesn't produce radioactive waste. So it's something in your lifetime that I hope you will see towards a sustainable future.
Thank you so much. So on behalf of VIT Bhopal University establishment, the administration and management, I heartily thank Dr. Helen Mason for accepting our invitation to be a part of this National Science Week celebration. And a special thanks to Professor Zeri from Physical Research Laboratory for his special appearance in our today's program, and all the participants for joining us that late evening of on this that special day we have today, this Mahashivratri, the special occasion of Mahashivratri. So for the participants, there is one announcement that tomorrow we will be having one session by Dr. Nakul Parashar. He is the director of Vigyan Prasar. That is an autonomous organization of Department of Science and Technology and Technology. So Government of India, and he will be speaking on the scope of science communication, popularization and extension tomorrow at 2:30 p.m. So once again, I thank you all.
Can I just say something before you close, please, Sharad?
Yes.
Yeah, I'd like to thank everybody for listening so attentively. There are many questions in the chat that I see, and I haven't been able to answer them. If you send those questions through to me, then I will answer them, because there are some very interesting questions. So I want to thank everybody, and the students in the schools and the students at the university and the teachers for engaging. I very much enjoyed speaking with you all.
Thank you. Thank you so much. Thank you. So once again, I thank you all for being such a great speaker and the audience at the same time.